Hey guys, I apologize. The last video cut out before I could finish my example, so I'm going to rework the last portion here. Um, the cart is upside down, and at the top of the loop, and then also I want to talk about the situation where um, you almost lose contact. So when the apparent weight is zero, you feel like you're just floating there at the top of this loop, going around the roller coaster, and we'll see what happens. And so I don't know when you're actually watching this. So I went ahead and wrote down the numbers we found before for when the person was at the bottom of the loop. I chose bad numbers, and so we almost certainly have killed somebody. But I guess they're not around to complain. So we'll go ahead and see what the corresponding forces will be at the top. We are expecting that the apparent weight is smaller at the top because if you think about a roller coaster, when you go upside down, what you feel is the real concept is apparent weight. That's the weight that you feel, and truly that just means the normal force. So okay, so the plan is to resolve this problem at the top of the roller coaster loop and identify the normal force. And we're expecting the result we found before. Just one second. I need my calculator to do this, I'm sure. Well, I don't have my calculator today, so we will just make do with what we've got. Okay. This is a force problem. As always, the starting point for a force problem is to draw the free body diagram, identify the forces, worry about coordinates and trig and stuff. This problem doesn't have much as far as complications. It's actually a very simple problem. So let's get started. Here's a person. Here's the free body, and there's also a weight force which acts down. I'm going to make my dot a little bit bigger. Okay. So there are two forces acting on my person as I go around the loop, and they both are in the same direction. I'll go and just work in the vertical. Really write down the net force in the vertical direction is minus mg from the weight and minus the normal force. By writing it that way, I'm actually solving for the magnitude of the normal force because I'll have a positive quantity when we're all done. The actual force points down. Newton's second law, that must equal the mass times acceleration. And here, because it's circular motion, we're looking at an acceleration of v squared over r. So I can rewrite this. I can say minus mg minus the normal force, excuse me, equals the mass times acceleration. That's mv squared over r. But remember, the acceleration is towards the center of the circle. So I'm going to have minus mv squared divided by r. Okay, very good. We know the mass, we know g, we know the speed, and we know r. So we have all the numbers we need. We just rearrange this to say that the normal force equals mv squared divided by r. So let me let's in my head here, since I failed to have my calculator out. This gives me the mass is 80, the velocity is 30, so 30 squared, divided by the radius, which is 15. So I factored out the mass. Now, if I think about that, 30 squared divided by 15 is the same as 2 times 30. So that's a 60, and 9.8 is 60 minus 10 should be about 50. And in particular, if I add in the details, it should be, oh, and then I have to multiply by 80. So I should have, this is about 50 times 80. So that's going to be 4,000 approximately. So approximately 4,000 newtons in round numbers. It's probably not that bad of an estimate, to be quite honest. So comparing with our previous result up here, when we found for the person at the bottom of the loop, the normal force, the apparent weight would be smaller. It's only 4,000 newtons, which is, they're still dead, but I guess it's less dead. If I had chosen better numbers, it would have been a better example. Okay. So next, the last thing I want to do in this little video is to sort out and study when something feels weightless, where the normal force would be 0. Because remember, apparent weight is normal force. It's not really weight. So when you talk about weightlessness, we're talking about normal forces. So we want to do the same basic problem at the top of the loop. The normal force equals 0. All right, same free body diagram. I have a normal force going down, a weight going down, F net equals normal force downwards. So the normal force I'm solving for would be 0, although we're going to set this. It would be, that's the same formula we just had 20 seconds ago. And now I want to set that equal to mass times acceleration. So just as before, I get minus n minus mg equals minus mv squared over r. Same as what we just had for the person actually going around getting squashed at the top of the circle. But what we want here, because we want to study when is the normal force equal to 0, or more in particular, that's not the right way to say it. Gives the normal force equal to 0. That's what we want. At what speed would the cart have to go around so that you feel weightless at the top of the loop? Okay. So to solve for that, all we do is set the normal force to 0, and we just solve. V squared over r, cleaning it up a little bit, we learned that V must equal, so the speed, the square root of g times r. And for this example, g is 9.81, r is 15. R is 15 in our circle. And well, we know that 12 squared is 144. And we know that 13 squared is 169. So we're a lot closer to 12 squared. So I'm going to guess just a shade over 12 meters per second. Um, so it's just a shade over 12. So approximately 12 meters per second. Okay, so at least 2 digits, that should be good. Very good. So what we find per second, when you got to the top of the loop, you'd feel weightless, like you just, and then dives down. You lose contact with the surface, so you feel weightless. Well, here the critical speed is 12 meters per second. So if you go faster than 12 meters per second, there is a normal force, excuse me, and you feel pressed against the cart. If you travel good, you're just going to fall off, or you're going to lose contact. And depending on how bad it is, you might like fall out. Okay. So wear your seatbelt. All right. See you guys next time.